We're pleased to have Maria Charisi with us, most lately of NANOGrav, which is a collaboration of looking at pulsar timing arrays, of which she will speak. So I won't say more about that, but most excitingly, she's coming here in January for her first semester. And then she's our newest assistant professor, and we're just super excited to have her join the department and super excited to hear about this update. So she's going to tell us all about the pulsar timing arrays. Thank you.
Thank you. Thank you for the invitation, and I very much look forward to joining and meeting you all in person again. Today, I'm very excited to share some amazing results that we published over the summer on the evidence that we found for the gravitational wave background pulsar timing arrays. So in astronomy, everything we knew about the universe until 5 or 10 years ago, it came from light. So initially, we started observing the optical band. We had a very limited sliver of the electromagnetic spectrum, and we had limited information. But as we developed more technology, we managed to observe through the electromagnetic spectrum from the lowest energy photons in radio waves up to the most energetic photons in gamma rays. And we uncovered a much more rich picture about the universe, finding very energetic phenomena like gamma ray bursts, but also even the beginning of the universe, the cosmic microwave background. From 2015, we have yet another way to observe the universe, and this is through gravitational waves. And this shows the first detection, the first direct detection of gravitational waves from two merging black holes. And this was from ground-based detectors like LIGO. Now, before I get to the gravitational wave spectrum, I want to give like the 2-minute introduction of what gravitational waves are. So gravitational waves are a prediction of general relativity, which is a geometric theory of gravity. And in general relativity, we have space-time, and when we have an object that has a mass, it curves the space-time. And then when we have an object that is moving through a curved space-time, it's the curvature of space-time that pretty much dictates how that object moves. And this is the equation of motion in general relativity, pretty much the F equals ma in GR. So the matter tells space-time how to curve, and then this part here, it tells matter how to move in a curved space-time. So one of the predictions of general relativity is the existence of gravitational waves. These are perturbations in space-time itself, and they happen when we have masses that accelerate. So every mass that is moving with an acceleration, it produces gravitational waves. These waves in general relativity propagate at the speed of light, and they're also transverse waves, and they squeeze and stretch space-time. So if we have a gravitational wave coming through me, it will squeeze me and stretch me in a way that it will make me taller and thinner, and then shorter and fatter periodically. Now, gravitational waves are very weak, and that means that we cannot observe them very easily. We need extreme objects like black holes or neutron stars to produce very strong gravitational radiation so we can detect them. And one of the things that is worth noting is that as gravitational waves are emitted, we have loss of energy from the system. So we have acceleration of the orbit, increase in frequency, and eventually the two objects, let's say the two black holes, will merge and become a bigger one, and the event will stop at the maximum frequency. That maximum frequency depends on the total mass of the system, and it's actually inversely proportional to the total mass of the system. So if we have low mass systems like stellar mass black holes, we have high frequency gravitational waves. But if we have high mass systems like supermassive black holes, we have low frequency gravitational waves. And of course, in the universe, we know that we have a variety of black holes with very different masses. So we expect that we have a gravitational wave spectrum that spans several orders of magnitude in gravitational wave frequency. And of course, unlike the electromagnetic spectrum, that it took us centuries to open new windows into the different parts of the spectrum, gravitational wave astronomy is very accelerated. So we already have the first evidence for the next big window into the gravitational wave spectrum. So I'm going to dive a bit deeper into the gravitational wave spectrum here. So what I'm showing is the gravitational wave strain, which quantifies how the space-time is squeezed and stretched as a function of frequency. So the first window we opened was the high-frequency gravitational wave band, where the ground-based detectors are sensitive and where we detect binaries of stellar origin. So LIGO has been operating for several years now, and it has given us a lot of excitement. It has detected about 100 black hole binaries, and then a handful of black hole neutron stars, and neutron star binaries, and even a neutron star binary with an associated electromagnetic counterpart. So this was pretty much the entire list of detections we were expecting with LIGO, and we got them all very efficiently. Now, if we move down in frequencies, we have LISA, and LISA will be a gigantic interferometer like LIGO, but it will fly in space, and it will be sensitive to millihertz frequencies. And LISA will detect the most massive of the stellar mass binaries that LIGO can detect, the least massive of the supermassive black hole binaries that I will talk about in a minute, and also another class of sources, which we call them extreme mass ratio in spirals, so pretty much small black holes falling onto supermassive black holes. I'm not going to talk about LISA today, but there is a review that we wrote with the entire astrophysics working group of LISA that pretty much describes all the astrophysics we can do when LISA comes online, and LISA is expected in the mid-2030s. Now, most of the talk will be in this final band of the gravitational wave spectrum, which is sensitive to nanohertz gravitational wave frequencies. And this is the Pulsar Timing Array band. So Pulsar Timing Arrays are a galactic-scale detector. Over the summer, we have announced that we have found the first evidence of a gravitational wave background produced by many supermassive black hole binaries. And hopefully in the next few years, we will detect even individual supermassive black hole binaries. Now, for this talk, I will first introduce the source population of pulsar timing arrays. So what are these supermassive black hole binaries, how they form, why they're important. And next, I will talk about pulsar timing arrays, the evidence we found for the low frequency gravitational waves, and also our expectations for finding individual binaries and eventually combining them with electromagnetic observations and doing multi-messenger science. So what are supermassive black hole binaries? We know from observations of nearby galaxies, like our closest neighbor here, the Andromeda galaxy, that every massive galaxy has a supermassive black hole in the center. And when I say supermassive black hole, I mean something that has a mass between 1 million and 10 billion times the mass of the sun. That black hole in the center is a very important component for the galaxy. We also know that through the history of the universe, galaxies merge quite often, and that process builds up the galaxies, so it makes more massive, bigger galaxies. But also, naturally, when we have a galaxy merger, we end up with a galaxy that has two supermassive black holes, one from each parent galaxy. And then as the galaxy merger progresses, the two black holes lose energy and move to closer and closer separations. So when they get to a parsec separation, so that's roughly a few light years, the two black holes become gravitationally bound to each other. And this is the state that I will refer to as a binary. Now, this entire process of galaxy mergers takes millions or even a few billion years. So for our human timescales, it's impossible to see the evolution of these systems. But of course, like everything in astronomy, especially in understanding galaxy evolution, we see many, many galaxies out there. And by catching the galaxies in different evolutionary stages and seeing the different snapshots, we can piece together the evolution of these systems. So for the last, let's say, 4 decades, we roughly know the main steps that two black holes take after a galaxy merger happens. So initially, we have the two black holes falling towards the common gravitational potential of the newly formed galaxy. Through a process called dynamical friction, these are large-scale interactions with the stars and the gas in the newly formed galaxy. And that process is efficient at removing energy from the system down to a few parsecs. When we get to about parsec scale, let's say from 10 parsecs to 0.1, the immediate interactions with the environment of the binary become important. So for example, if we have stars that cross the orbit of the binary, so we have three-body interaction, the star will be expelled to large distances. So the star gains some energy, and the binary has to lose some energy for the energy to be conserved. Of course, the star is very small compared to the supermassive binary, so we need many, many such interactions to bring the binary to smaller separations. And it has been an open question whether there are enough stars around the binary to bring the binary to the small separations. Another potential, let's say, mechanism that removes energy from the system is if we have gas. So it's possible that when the galaxies merge, we have gas involved, and there's gas around the binary that can also remove energy from the system. Now, if and when they get to small separations, the gravitational wave emission becomes dominant and drives the binary to the final coalescence. Now, among these 3 steps, the intermediate one is the one that has remained the most uncertain for decades. And the reason is that we have never observed the binary at a sub-parsec separation. And it's very challenging to observationally confirm these systems, but this detection that we announced over the summer could be one of the answers to this problem. And I'll come back to that in a bit. So I can take a short break and see if anyone has questions about the intro stuff before I get to the detections.
Anything in the chat?
Yeah, I don't know. Maybe Maria can check the chat. I think actually the audience online outnumbers the audience in the room.
Okay, I don't see anything in the chat, so I'll keep going. Now let's get to pulsar timing arrays and how we can use them to detect gravitational waves from supermassive black hole binaries. So pulsar timing arrays are rely on millisecond pulsars. So these are neutron stars that have, oh, now I see a question. Okay. No, it's not a question, it's just a comment. We have neutron stars, which are very dense stellar remnants that have magnetic fields. And along the magnetic field, we have collimated electromagnetic emission. So we have a beam of radiation. And these neutron stars are very stable rotators. So if the rotation axis is misaligned with the radiation axis, we get this lighthouse effect. So every time the beam swipes through our line of sight, we get a pulse that we can record with radio telescopes. And because these neutron stars rotate very stably, we see the repetition of the pulses very, very precisely and periodically. Now, this is a highly exaggerated signal because pulsars give out very weak signals. So we need access to the biggest telescopes around the world. And for that reason, we require a lot of telescope time and many people working on this project to finally make it work after about 2 decades of work. So in the US, we have the NANOGrav collaboration, which stands for the North American Nanohertz Observatory for Gravitational Waves. NANOGrav currently uses mostly the Green Bank telescope, but we had about 15 years of Arecibo data before it collapsed. And now we are moving to other telescopes like CHIME in Canada and the VLA and some other telescopes that hopefully will start operating in the near future. And I've been a part of NANOGrav for over 6 years now. In Europe, there's the European Pulsar Timing Array, and there is an array of telescopes around Europe. In Australia, there's the Parkes telescope mainly, and we have the Parkes Pulsar Timing Array. And more recently, we had the formation of some newer PTAs, the Indian Pulsar Timing Array, the Chinese Pulsar Timing Array, which use a gigantic radio telescope called FAST. And we also have one Pulsar Timing Array in South Africa called the MIR, the MPTA, because it uses this MIR time telescope. Now, how do we use all the data we collect from these telescopes to find gravitational waves? So let's say we have gravitational waves that were produced from a galaxy merger that passed through our own galaxy. And they squeeze and stretch the space-time between the pulsars and the Earth. So some of the pulses will have to travel shorter distances until they arrive to the Earth, and some will have to travel longer distances. So instead of getting this precisely periodic profile, we have some pulses that arrive earlier and some pulses that arrive later. And we need to see this signal in many, many pulsars in the galaxy, because if we see it in only one, it could be something weird that the pulsar is doing. And here's an animation from the press release, which shows the precise locations of the pulsars that we time and our location in the galaxy. So we need to detect this signal in many of the pulsars. And we also need that this signal is correlated among the different pulsars. So this is called the Hellingston-Downs curve, and it shows the degree of correlation we expect among pairs of pulsars as a function of the separation, the angular separation in the sky. And this has a quite complex mathematical derivation, but I'll try to give you, to help you build some intuition. So let's say we have two pulsars from the same part of the sky. The two pulsars will experience the squeezing and stretching of space-time simultaneously. So their signals should be positive correlated. Then let's say we have two pulsars that are at 90 degrees. So one pulsar will experience a squeezing, the other one will experience a stretching. So the signals from these two pulsars should be anti-correlated. Now let's go again to 180 degrees. The two pulsars experience squeezing and stretching simultaneously, so we go back to positive correlations. So this is the expectation from general relativity. And this is what we announced at the end of June this summer. So what we see in NANOGrav with the 15-year data set, so we have data from 68 pulsars and an observation time span of 15 years. And we see that all pulsars show evidence for gravitational waves, like the coherent deviations that I was describing before. And also we see that the correlations between the pairs of pulsars roughly follow what we expected from the predictions from GR. The significance of this is 4 sigma, and we decided not to call it a detection. So we will adhere with the particle physics standards and wait until it's 5 sigmas. That's why we're calling it evidence for a gravitational wave background. But we think that by the nature of this experiment, as we time more pulsars and for a longer time, the significance of this evidence will grow. Now, of course, as I said, we are not the only collaboration that is doing this type of science. The Parkes Pulsar Timing Array collaboration that times about 38 pulsars for 18 years found a significance of about 2 sigma for these spatial correlations. The European Pulsar Timing Array, combining data with the Indian Pulsar Timing Array, they have about 25 pulsars and 24 years of data overall, but for this analysis, they used the last 10 years of data because it's higher quality. And they found a 3 sigma significance. And the Chinese Pulsar Timing Array, which has about 57 pulsars, and it's relatively newer, so it has a smaller time span, they claim to have a significance of 4.6. I said they claim, and I'm not going to get too much into the politics, but their data are not available to us to reanalyze and see if we find the same significance. After we, like each individual PTA announced their results independently, we also analyzed the results from the 3 main regional PTAs as a common data set, and we find that the results between the different PTAs are consistent. Now, why is this important? Okay, we open a new window into the gravitational wave spectrum, but this signal has a lot of astrophysical information. So if we assume that the background that we see is from a population of binaries that are in circular orbits and they evolve only due to gravitational waves, we expect that the strain as a function of frequency will be a simple power law, which is the gray shaded area that I'm showing here. However, if we have other mechanisms like the 3-body interactions with the stars or the gas that also contribute to the evolution of the system, because there is an extra mechanism, the system at large separations, meaning at small frequencies, it evolves faster. So we have fewer systems at the lower frequencies, and instead of having this power law, we have a turnover at the lowest frequencies. And also, if we have eccentricity, that will also be imprinted on the gravitational wave spectrum. So by constraining first the amplitude, at what level is this power law, we can have a handle of how often galaxies merge, how massive are the black holes in these galaxies, and also how efficiently the binaries overcome that final parsec problem that I was describing in the beginning. And also by constraining the shape, we can figure out if there are additional mechanisms in play, and also if the binaries are typically circular or eccentric. So in the astrophysics working group, we set out to interpret the results we got over the summer, and this is one of the papers that I played a significant role. So what we did was first to build population synthesis models. So starting from the galaxy mergers, populate them with supermassive black holes, use whatever observational constraints we have from other methods, and then eventually evolve the binaries from the large separations down to the gravitational wave regime, and then make a prediction of how the gravitational wave spectrum should look like. This is, first of all, this has a lot of uncertainty. And second, this is fairly expensive to build this model. So we decided that we would sample and make many populations of its, let's say, parameter, and then interpolate using Gaussian processes. So the details are not important, but eventually we get, with theoretical expectations of the gravitational wave background, which then we can compare to the observed data and infer something about the population of binaries that produces that background. Now, what we learned is, first of all, the binaries can produce the gravitational wave background. So what I'm showing here is, again, the strain of the background as a function of frequency. The gray violins, as we call them, are the gravitational wave data. So this is the data where we find evidence for the background. And then the different curves here are the different astrophysical models that we explored. So if we look at the model that assumes that all the binaries evolved due to gravitational waves, which is the purple here, and we compare with models where the binaries interact with their environment, you can see that the blue and orange here fit better the data. So probably it's not only gravitational wave driven interaction evolution, we also have effects of the environment at play. Now, if this is if the signal is coming from binaries, and that's the most likely explanation, this is the best evidence that we have that the binaries indeed form and overcome this final parsec problem, because if they stalled at the parsec scale, they wouldn't be able to produce this level of the signal. Now, another thing to keep in mind is that it's still the early days. The signal we have, again, we don't even call it a detection, it's at the low signal to noise ratio regime. So we expect that as we characterize the background better, things will change and our understanding of the background and our inference on the background will change. Now, one thing that is unlikely to change is that the amplitude of the gravitational wave background is relatively high compared to what we previously expected. And here what I'm showing is the constraints we have for the background using some different data analysis methods. And these are the theoretical predictions we had, and the same is here. So at a reference frequency of 1 over a year and at a reference frequency of 1 over 10 years. And you can see that what we observe, which is the green or the gray shaded areas, are at the high end of what theorists had predicted before. So that means that either galaxies merge more often than what we expected, or the black holes in these galaxies are more massive than, again, what we previously expected. So the black hole mass is typically correlated with the mass of the galaxy. We don't have to make these assumptions about the galaxy merger rate or the black hole scaling with the galaxy mass extreme, but they have to be at the high end of what we expected. Of course, there's a hidden sociological reason of why the models are under-predicting the background, because in 2015, there was this idea that we haven't detected the background yet and we will never detect it. And the theorists started becoming, let's say, more inspired to push their predictions to smaller and smaller values. But I think what we see typically is higher than what we expected. Now, again, I said, if this is coming from binaries, and in my opinion, and probably in all of the astrophysical community's opinion, this is most likely coming from binaries, but there is also ideas from the cosmology side or from new physics that could cause this signal, and they have to do with gravitational waves from inflation, cosmic strings, and this is far from my expertise, but we did this analysis, and this is something the cosmologists are very excited about. So we found no evidence for new physics beyond GR, but it's not that we can rule them out either. So there's only a small part of the models which assumes stable strings that cannot reproduce the background. But again, as we characterize the background better, probably these constraints and whether this is coming from supermassive black hole binaries or from something cosmological or from new physics will become more clear. And again, I can see if I have a question on the chat. How often does gravitational wave evidence from a pulsar appear in observation? So the thing is, it has to appear in all the pulsars, and it has to be correlated among the pulsars. And it took us about 2 decades to find this evidence. So pretty much it happens in every pulsar, but it's very hard to tease it out from the noise. I can see if there's another question here before I move on.
Good question here.
Yeah, go ahead.
Okay. Just so was I understanding that right, that this is nanohertz detection?
Yes.
If so, that, I mean, it comes out to be about 300-year periods. Is that directly, is that right, something like that?
So the periods are roughly between, let's say, 15 years. What determines so there are two things. The frequency of the gravitational wave background is twice the orbital frequency of the binary. And then the window we can probe, if you think of this as timescale, let's say, the lowest frequency corresponds to the longest observational time span, which is 15 or 16 or 18 years. And the shortest depends on how often we time the pulsars, which is roughly 2 weeks. So the window we can probe is from 2 weeks to 15 years.
And do those frequencies correspond to, the periods do correspond to the periods of, except with a factor of 2 of the binary
Yes.
orbiting?
Yes, exactly. With a factor of 2, they do. There's another question, I think, in the chat. Yes. So whether I can comment on the pulsar glitches. So yes, the glitches are a problem, but because we time millisecond pulsars, we typically select the most stable of the pulsars. So some of them do glitch within the 15 years. And I'm not a neutron star expert, but people do think a lot about this. And this is the reason we only use 68 pulsars and not like the hundreds of pulsars that we know. So we select very carefully the most stable clocks.
Maybe I can ask a quick question. Among the whatever 58, 47, pulsars used by different PTAs, I guess there are just a handful that are really driving the error bars down here. The question is, those few pulsars, are they present in all the PTAs?
So there are some pulsars that drive there are some pulsars that are common among the different PTAs, and there are pulsars that are timed from each regional PTAs that is not in the other data sets. But what really drives the significance of the signal is that we have many pairs to do the cross correlations. And there's a figure in the detection paper that shows that as the number of pulsars that we time increases and the number of pairs increases accordingly, that really boosts the signal significance, because then it's very hard to do it by chance.
Yeah, I mean, they're not that independent observations, except that, of course, the noise is different, but not the pulsar noise. But anyway, we can return to that.
Yeah, I mean, what do you mean by they're not independent observations? Because we have similar pulsars in the, okay, yes. Yeah, that is true. And actually the next step is to combine the different data sets. So when multiple PTAs have data for one pulsar, it will be combined in one. And then I guess that will be accounted for.
Sure.
Okay, if there are no more questions, I can move to what I think is a very exciting future, and that means the detection of individual binaries and then the detection of electromagnetic waves from those. So from the beginning, we expected that pulsar timing arrays will find two main signals. One is the stochastic background, which we have already found evidence for, and that comes from the superposition of many unresolved binaries. And the second type of signal is to find individually resolved binaries. So these are, let's say, the loud voices in a crowded restaurant. So these will come from very massive and relatively nearby binaries, and they can be resolved on top of this background. So we typically catch these binaries very early on, before like tens of thousands of years or even hundreds of thousands of years before they merge. So practically for us, they're a binary that stays at the same frequency for the entire time that we can observe. So it's a monochromatic, let's say, gravitational waves. Now, if we detect this type of signals, we can be more and more confident that the background we have detected is not cosmological and it's coming from binaries. And according to the theoretical models, we expect to get to the detection of an individual binary 3 to 5 years after we detect the background. So maybe in 3 to 5 years or in 4 to 6 years, depending on how you count the detection. And of course, in every data set that we publish, we also search for the individual, the gravitational waves from individual binaries. So far, we haven't found any. So we have placed constraints on the strain from individual binaries, and this is the sky map of our upper limits as a function of the position. So the stars here show the pulsars that we have in the NANOGrav 15-year data. And you can see that at the part of the sky where we have more pulsars, we have better constraints, so we can place more stringent upper limits. And we can use that to do astrophysics, say which galaxies, if they hosted a binary, they could produce detectable gravitational waves. And since we haven't detected something, what kind of limits we can place on these binaries. So this is a paper I led for NANOGrav a few years ago with the previous data set. And what we did was practically what I described. We took this map, we found which galaxies are within the sensitivity volume, and then we can use our gravitational wave data to place a constraint on the strain. Then having some information from that galaxy, for example, what is the mass of the central black hole, or what is the distance of the galaxy first, we can place a constraint on the mass of the system, on the chirp mass, and then that chirp mass depends on the total mass and the mass ratio. If we have a measurement for the mass of the central supermassive black hole, we can convert that to a mass ratio upper limit. And the important thing is, like, for some of the best galaxies in our sample, we can place very important constraints on the mass ratio. So if there is a binary in these galaxies that we explore, the second black hole has to be much smaller than the first one. And the interesting thing is that even with the 11 years data set, which is what I used for this paper, there are galaxies where we can place constraints that are comparable to the constraints we can place for a binary in our own galaxy with other independent methods. And of course, as we get to more sensitive data sets, like the 15-year data set, that these limits go down. And of course, our goal is not just to give interesting limits, but also to get to the detection. And for me, the most exciting prospect when we get to the detection is that then we can do multi-messenger science. Because we think that these systems also, except for strong gravitational wave emission, they also emit strong electromagnetic emission. And the reason for that is that when we have galaxies that are merging, we also have a lot of gas that is involved in the process. And that gas is pushed to the center of the post-merge galaxy that can fall into the black holes and can produce bright electromagnetic emission. So this emission provides electromagnetic signatures that can allow us to find these systems with a completely different method, not only with pulsar timing arrays. And of course, there are two routes to get to a multi-messenger detection, and as I will describe in a bit, I'm very interested in both. So the first approach is to find electromagnetic candidates, and I will describe in a minute how we can do that. And then pretty much target our pulsar timing array detector and find gravitational waves from these systems and confirm that these are binaries. The second option is that we find a gravitational wave event, and then we need to find the electromagnetic counterpart. So find from which galaxy this is coming from. Now, why is this important? Because each messenger carries different information about the system. So the gravitational waves pretty much probe the orbit and the dynamics of the binary. whereas the electromagnetic observations probe like the conditions of the plasma and how the binary interacts with the gaseous environment around it. So if we combine the two, we can get the most complete picture of the physics of these systems. And another, like from a practical standpoint, if, let's say, when we do a gravitational wave search for individual binaries, we typically do a completely uninformed search. So this is what we call a blind all sky search. But say we know something about a candidate, let's say we know from which galaxy it's coming from or what is the period of that system, we can go from a sub-threshold detection. So what I'm showing here is the detection probability or the detection significance of simulations. We can go from something which is very low, sub-threshold, to something that is significant. So we can accelerate, let's say, the detection timeline by this. And even if we don't find gravitational waves, just by pointing to a specific galaxy, we can improve our limits. Now, I'll open a parenthesis to describe how we can find these systems using electromagnetic waves for a second, for a few minutes, let's say. So the most promising method is to find quasars that have periodic changes in their brightness. And quasars are bright galaxies for which the supermassive black hole in the center is fed with great amounts of gas. And we think that at least some of them are activated by galaxy mergers, so that makes them good places to look for two supermassive black holes. And now for the periodic variability, I would say this is fairly intuitive. We have an orbiting binary that periodically perturbs its environment. Sorry. So we expect periodic changes in the brightness, but this is something that has been confirmed over and over in hydrodynamical simulations. So when we put a binary in a gaseous disk and we evolve the system, typically we see two mechanisms to produce these bright periodic changes in their luminosity. One is that we have these streams of material that periodically come to the black holes. So if we look at the accretion rate or the feeding rate of the black holes, we see periodic modulations at the orbital period of the binary. The second possibility is because we have gas that gets trapped around these black holes, it becomes bound, and it moves with relativistic velocities. We have effects from special relativity. So for example, if we have a relatively unequal mass binary, the smaller black hole typically has a much brighter disk, and it's the one that is moving faster. So when the smaller one moves towards us, it will appear brighter. When it moves away, it will appear dimmer, and that produces sinusoidal periodicity. Now, the general conclusion is that these systems can produce very bright luminosity that is at the level of quasars, and also this luminosity can be periodic. And over the last, let's say, 8 years, we had a lot of development in this field, because for the first time we had a lot of data that we could do the search for periodicity in quasars. And that includes my thesis work with the Palomar Transient Factory, which found 33. It was one of the first ones back in the day. It found 33 candidates. So now we have analyzed pretty much all the time domain data from the surveys that we have available. And we have found about 250 candidate systems. Of course, I'm emphasizing the word candidates here because finding periodicity in these quasars is very hard. One of the reasons you can already see here, so the periods we are looking for are relatively long, and we cannot see many repetitions of the cycles of periodicity. The second is not as obvious. It has to do with how the typical quasar that has even one black hole varies, and because it has stochastic variability, it can mimic this periodicity that we see, especially in the limit of observing very few cycles. Now, confirming even one of these systems is really a big deal. And we can observe for a very, very long time and collect the required amount of cycles that can take decades. Or the other possibility is to look for additional signatures in, let's say, multi-wavelength data or other kinds of data to convince ourselves that there are multiple independent lines of evidence that there is a binary in that system. So I'm showing here a snapshot from a recent review that I wrote with Dan Dorazio, where we collected all the potential observational signatures of binaries. So this is in terms of the binary period and the total mass. And you can see where the periodic, the quasars with periodicity fall. And then we have other signatures that we have to do with the jets or the gravitational wave emission here and here, or the spectra of these systems and other. And you can see that there are candidates where we have overlapping signatures. So the bottom line here is that there are several candidates that show multiple independent lines of evidence that they are binaries, but unfortunately these signatures are not unique. Hopefully with better data, we can convince ourselves that some of these systems are indeed binaries. Now, this is a very exciting time because we have the Rubin Observatory that will start operating in just next year. And Rubin will be a complete game changer for searching for quasar periodicity and supermassive black hole binaries for two main reasons. One is that the data quality is much better than what we currently have. And the second is that LSST, or the Rubin Observatory, will find many, many more quasars, 2 or 3 magnitudes more than what we currently have. And this huge sample, we expect to find even some of the more rare binaries that have periods of a few months, let's say. So if we can detect a binary that has a period of 2 months over the course of the 10-year survey, we can collect many, many cycles, and we can be certain that this source is periodic and indeed a binary. The other exciting thing is, of course, that because we expect to have this kind of short period binaries, we can even detect them in the next few years from the first time that the Rubin Observatory releases the data. Now, what I'm very excited about is that these time domains in the quasar periodicity that I've worked quite a bit on can work very synergistically, can work very well together with the pulsar timing arrays. So pretty much the time domain surveys and pulsar timing arrays can probe the same population of binaries. So what I'm showing here is a plot from a recent paper where we looked at which binaries we can probe with both methods in terms of the total mass of the binary, the period of the binary. So the blue shaded region shows binaries we can detect with electromagnetic waves. There are some assumptions in the model. And the purple shaded region shows binaries we can detect starting from the NANOGrav 11-year sensitivity, which was the last one that was published like 1.5 years ago when we published this paper, to projected sensitivities for the International Pulsar Timing Array in just 2 years in the future. So roughly the sensitivity we have here is around here. And then the sensitivity we will have with the square kilometer array in, let's say, 10 years down the line. So currently we are limited to the most massive binaries. So we can detect them with pulsar timing arrays and also with electromagnetic observations. But as the sensitivity of PTAs increases, the common parameter space becomes more significant. And the idea here is that, again, because each signal carries different information and has different dependencies on the binary parameters, if we combine them, we get more information out of this. So what I'm showing here is something that I'm working on right now. So these are simulated data. So we have the same binary. We simulate the gravitational wave signal and the corresponding electromagnetic signal. You can see what I already mentioned, that the frequency of the gravitational wave is twice the orbital frequency of the binary, which is, again, the frequency of the electromagnetic wave. And then if we analyze each signal independently, for example, from the electromagnetic wave, in terms of mass ratio of the binary and total mass, we get these constraints for these two parameters. For the gravitational waves, we get something different, and then we put them together and we get the best constraints. So I'm currently developing a pipeline to combine these two distinct data sets in one single data stream. Now, for the last, almost the last slide, I wanted to describe very briefly the other possibility of getting to multi-messenger detections, which is to find the gravitational wave first, and then find the host galaxy. And this is something we've been working with Paulina Petrov at Vanderbilt. So we are simulating pretty much the first discovery of gravitational wave. And then we calculate how well localized that signal will be. And then we find how many galaxies we have in that error volume. And you can see that we expect that the first detection will have relatively poor localization. You can see that this is a significant part of the sky. And we can have many, many galaxies, which are the cyan dots here within that error volume. But the good news is that the galaxies we are sensitive at, they are very massive. So they're very special galaxies. And if we do cuts based on the distance and the mass we expect from the gravitational wave signal, we are left with the dark blue points. So we are left with a handful of galaxies, which is manageable. And of course, we want to think more how we can start ranking these galaxies and eventually get to the correct one. So we are still quantifying this, and there's a lot of more work that we need to do. But this is a very exciting time to be doing this. So I'll finish with what we expect for the next few years in this field. And I think this is a very exciting time to be studying supermassive black hole binaries. So we start with the gravitational wave background. We have already found evidence for this background, but I put some years here just for the people who want to get the 5 sigma detection. Then from next year on, we will have LSST operating, and we expect to find many supermassive black hole binary candidates using electromagnetic data. Then the next big milestone in PTAs is to find that one single binary that is strong enough and sticks above the background, find the host galaxy, or find the gravitational waves from the electromagnetic candidates. And then eventually, over the course of the decade, we will have characterized the gravitational wave background better, and we will find a population, hopefully, of binaries from the Rubin Observatory. And then in the mid-2030s, we have LISA flying, and this is yet another window to the gravitational wave spectrum, probing different frequencies and different masses of supermassive black hole binaries. And with that, I'll just leave you with the summary, and I'll take any questions.
Yeah. We have time for a question or two. Just in terms of the pulsar timing arrays, I'd like to know, are we limited? What do we need for better progress there? Do we need basically more telescopes and more radio telescope time? Or do we need the pulsar population to be more cooperative with more stable pulsars?
We need both. We need both. If we have more pulsars that have good quality data, that helps a lot. But we are also limited. You're right. We are limited by telescope time. Especially after we lost Arecibo, most of our timing currently happens in GBT, and there's as much time that we can get on that telescope. And this is exactly why having the international pulsars, the international partners that are timing pulsars with different telescopes helps a lot, because they can time different telescopes and we can coordinate how that happens.
So could I ask a question?
Yes, go ahead, Phil.
concerning the HD curve that you showed, I'm trying to understand something. Does the time shift depend upon the range of the pulsar? So in other words, when you do this correlation analysis, I'm trying to understand if the pulsar is farther away, then it's traveled, it will be influenced by the gravitational radiation longer. So I'm just, is that a factor that comes into this?
So the thing is, you have to think of this as a stationary signal, because these binaries stay in the same orbit for a long time. You can assume that this signal has gone through the entire galaxy, and every pulsar has been affected.
Okay, thank you, but we can extend the conversation some other time. Thank you.
Okay, sure.
Good. I don't see any more questions on chat, and we're a little short on time, so there's one question here. Last question.
So my question was, is the background GW radiation isotropic? And in the list of cosmological sources, there was no mention of GW sources from the Big Bang itself. Can that be a source itself?
So the first, at let's say the zero level, we assume it's isotropic. If it's coming from binary, and maybe that's our best hope to discriminate between the cosmological models and the astrophysical ones. So if it's binaries, it will be on specific galaxies, and it will be dominated by, let's say, some sources. So it's not going to be completely isotropic. Whereas if it's cosmological, it's going to be completely isotropic. So one way as we go forward to distinguish the two possibilities is to find an isotropy in our data. And if we find an isotropy, then we can start thinking this cannot be cosmological and start excluding that. So far, I would say the assumption is that this is isotropic, but as we characterize the background better, if we find an isotropy, it will be pretty much the smoking gun signature that it is from binaries and not from cosmology.
Thank you, Maria.